Welcome. Section 2.4, C operator precedence and associativity. This is a lecture on a section from the book Real-Time Computing for Mechanical Engineers, a Lab-Based Approach by Piccone, Garbini, and Devine. I'm Dr. Piccone. You can check out the book at the MIT Press website and at the companion website. Operator precedence and associativity. Throughout our C programs thus far, we have used operators like plus, equals, the assignment operator, and plus plus, the increment operator, in expressions such as x equals 9 plus 3. We mean by this that 9 and 3 should be added together and the result assigned to the variable x. We assumed that the plus operator has higher precedence than the equal operator, the assignment operator. Our assumption was correct, but it's because the C language followed our intuition about operator precedence and associativity. If, rather than adding 9 and 3 together and assigning the result 12 to x, the equals operator was higher precedence than the plus operator, we would have x assigned the value 9, and then we would add 3 to that value, but not assign the result to x. The table at right lists all C operators through the C99 standard in order of their precedence, highest to lowest. Operators within the same division have equal precedence. So, precedence 1, we have increment, we have function call parentheses, we have array subscript brackets, we have the dot member access via object name, we have the arrow operator member access via pointer, which we'll talk more about. And the compound literal all are the highest precedence. Next in precedence are the prefix, increment, and decrement. The highest was postfix, increment, and decrement. Prefix is before your variable. Unary, plus and minus. Logical not and bitwise not. Cast, indirection, the dereferencing operator. The address of operator, we saw these two used with pointers, right? Size of and align of all have precedence 2. 3, multiplication, division, and remainder. 4, addition and subtraction. And then we continue on down the list. So this table has essentially all of the operators that we will use in descending order of precedence. But notice that there are some that have the same precedence, right? And when they have the same precedence, we have to fall back to associativity to determine which operands will bind to which operators. Think of the compiler considering an expression and interpreting its meaning. The operators in the expression tell it what to do with the operands, but there remains the question of the binding of operands to operators. It proceeds to bind operands to operators in descending order of precedence. However, there are operators with equal precedence, like plus and minus. The associativity breaks the tie. Left to right associativity associates those operators of the same precedence from left to right. For instance, the left to right associative plus and minus operators have the same precedence, so 1 plus 2 plus 3 would be interpreted as, and we use parentheses to make the associativity explicit, 1 plus 2, that quantity plus 3. Mathematically, of course, addition is associative, both left to right and right to left, and this is compatible with the C syntax. In fact, all the usual math operators are compatible with mathematical precedence. For example, consider the following expression: 3 times 2 plus 1. this expression will be evaluated as 3 times 2, quantity plus 1. Because the multiplication operator has higher precedence than the addition operator. Returning to the previous slide, we see that the multiplication operator has precedence 3, whereas the addition and subtraction operators have precedence 4. So these two operands get bound with this higher precedence multiplication operator, and the result of 3 times 2 is bound to the plus operator. 1 is also bound to that plus operator, so it'll be 6 plus 1. Great. So that's basic precedence and associativity. Let's look at another example. What is the value of the following expression? From table 2.1, so the table above, we see that the precedence of the operators to the right of the equals sign, so the comparison equals, are equivalent to those of arithmetic. So 12 divided by 4 plus 2 times 9 minus 18. Therefore, the division, 12 over 4, and the multiplication, 2 times 9, will be performed first. The resulting expression could be simplified to 4 equals 3 plus 18 minus 18. The plus and minus operators have higher precedence than the equality operator, so they will be performed first. However, plus and minus have the same precedence, so the order will depend on associativity, which is left to right. Therefore, 3 plus 18 will be computed first, and then 21 minus 18, which yields 4 equals 3, which is of course false. This expression will evaluate to 0, representing false. And the footnote just observes the fact that for this problem, whether the associativity of plus and minus are left to right or right to left have no impact on the result. However, in some cases, that will not be the case. The associativity will change the result in certain cases. A final basic example of operator precedence and associativity. Example 2, determine the value x after the execution of each line in the following code. So we first initialize x, an integer, to 1. Then we go through a series of statements, and after each statement, we want to determine what the value of x is going to be. So we can just go ahead and make a program to directly compute this. We'll make a little print function that will print the value of whatever x is, which is what we'll pass to it, the value of x in main, and it will say x equals this integer. So after each statement, we simply print x and see what results. So after the first statement, x equals 1, we print it. It should say x equals 1. I forgot to include x equals 1 here, so this should say x equals 1. Okay, after the second line, we are going to print again. So let's see what happens. So x was 1, plus equals, we have 3 times 2 on the other side. Let's look at the plus equals operator. Remember, plus equals means take what's to the left of it and sum it with whatever is to the right of it and assign it to whatever is to the left of it, which is the variable x. So let's take a look at the table and review the plus equals and the multiply operators. So we have the multiply operator, which is precedence 3, the plus equals operator, which is down here, 14. Okay, so that's much lower. So we're expecting to bind with the multiplication first. So here we are back at our problem. 3 times 2 is going to be bound first. So we're going to have 6 on the right-hand side. So x was 1. we'll add 6, so we should get 7, resulting and assigning that to x. So sure enough, x equals 7. Okay, the next one we have plus. Plus was right below multiply in the precedence table, so it also has a much higher precedence than the minus equal, which is the same as plus equal precedence. So we'll do 9 plus 5, which is 14, and we'll subtract 14 from 7, which was what x was to start this line. So 7 minus 14 will give us negative 7, which is what the program prints. Okay, so we have negative 7 going into this next line. The multiply equals, also very low precedence, 14 as well. So 4 times 3 multiply is higher precedence, and we find that this is 12, and we multiply 12 and negative 7 to get negative 84. Good. Okay. Now we're going to do multiple things in one line here, multiple assignments of x. So let's follow this through. We have the x divide equals x plus equals 1. So we're going to make 2 assignments here, and we need to see which one's going to happen first. Divide equals or plus equals. Let's go back to our table. We have plus equals and we have divide equals. They're in the same level of precedence, 14. So to break the tie of precedence, we have to see associativity, right to left associativity. Okay, so that means that right to left associativity means that we're going to do this one first. So what was x starting this line? It was negative 84. We are going to add 1 to 84 and set that to equal x. So now we're going to have x equals negative 83 after that. Okay, so x equals negative 83. Now we're going to do the division equals. So we're going to have x divided by whatever is on the right hand side, which is also x. Okay, so it's going to be negative 83 divided by 83 and assigning that to x, which is going to be 1. So we get 1 as a result. So just to write this out, it was x divide equals, after we did this operation, we had negative 83, and x divide equals is going to divide x by whatever x is, which we just assigned x the value of negative 83 in this step. So assigned to x. So since we're going to have whatever this result is, it's going to be x. When we divide it by itself, x divided by itself, we're going to get 1. Okay, so that's the 1. Now we're going to do mod. So x is 1. So we're going to do x equals 1 mod 4. We have to check that the assignment operator and the mod operators have different precedence and interpret them. The assignment operator is here in precedence 14. The mod operator is precedence 3. So we're going to do the mod first. So we do the mod first, which is 1 mod 4. So 1 divided by 4 has remainder 1. So that's what 1 mod 4 is. 1 mod 4 is 1. We're going to take that result and say x equals 1. X equals the result, which was 1. So after that statement, we'll print x equals 1. The increment and decrement operators and their precedence. So these are a little bit tricky when you first look at them, so we'll take special care. As we have seen, the plus plus and minus minus operators increment and decrement an integer by 1. Each of these can be either prefix, for example, plus plus x, or postfix, for example, x plus plus. The postfix increment, x plus plus, and decrement, x minus minus, have high precedence, but it is important to note that the actual increment or decrement of the operand is delayed until after it is used in the expression. That's what the postfix means. So we use x and then we increment it or decrement it with the postfix notation. So in the statement y equals x times z plus plus, the current value of z is used to evaluate the expression, i.e. z plus plus evaluates to z, and z is incremented only after it has been used. This is the primary difference between the postfix and prefix increment and decrement operators. The prefix versions, plus plus and minus minus, increment before the value is used in the expression. Example 2.3, which will be on the next page, shows some interesting precedence interactions among the dereference and increment operators. So let's take a look at this. Determine the values of val, a variable we'll assign, the dereferenced pointer, dereferenced p, and the difference between the pointer p address and the initial address p0 after the execution of each line of the following code. So we have an array with 0 and 1 being the two values in the array. We have an int pointer, so we're going to point to an integer, which is going to point to the first value of the array to start. And we're going to have a pointer that will also be initialized to the first value of the array that we're not going to be moving. So p0 is always going to point there. And then we're going to have val be starting out as the dereferenced p, which is to say dereferencing the pointer to the first element of the array, which should be 0 to start. So we can go through this and line by line predict what val should be, what the dereferenced pointer should be, and also what the difference between the pointer address and the initial address should be for each step. So this program just directly computes this and prints these things out. So let's start. So the value, like we said, we initialized val to be 0. So value is 0. P offset is 0. Our pointers are both pointing to the first value in the array. And this is our initial case. So that's our first line. The second line is going to be the line in which we have the dereference p plus plus, postfix plus plus. And what this statement says is that the value will be 0 and the offset will be 1. So we have to look and see what is the operator precedence for the dereferencing operator and for the postfix increment. So let's go back to our table and take a look. We have the multiplication asterisk here, but the indirection dereference is here. So pretty high. The postfix increment and decrement, however, is higher. It's precedence 1. So we should get that happening first, although remember when it's postfix, the value gets used first, right? So going back here, we have the value of P getting used in the expression first, which is to say the pointer before it is incremented. So even though plus plus has higher precedence, it will not operate until after the value has been used in the expression. So we're going to dereference P first, and then we're going to increment the pointer. So the value should be of a dereferenced P. P was at the start of this pointing to 0, and it will be pointing to 0 for this execution. So the value here should be 0, and then afterwards it's going to increment the pointer. So then the pointer is going to move to be offset by 1 after this expression. So we should see val get the value of 0, and then we should see the pointer move to have an offset of 1. So that is what we see. The value is 0, and the offset of the pointer is 1. Okay, so we did this, we did this. All right, now we're going to start the next row. So we did this one. Now in this next one, the pointer starts out pointing here. So now it's over here. Pointer's there. We're going to, again, dereference P before we decrement it. So we're going to dereference this pointer, and that will point to 1. So the dereferenced value should be 1. And then afterwards, we're going to decrement it. So then the pointer should point to 0. So we should have 0 offset of the pointer. So let's see, we have a value of 1, and the P offset is 0. Good, just as we expect. Okay, so we did this, and our pointer is now back here. So now we have a dereferencing of a prefixed increment operator, a prefix plus plus on P. So they're both operating on this pointer. The plus plus is going to operate first. It's going to increment the pointer. Okay, so we're going to move it from the 0. So we're going to move it from pointing at 0 to pointing at 1. So that's, since it's prefix, it'll operate first. And then we're going to dereference. So it should dereference to a value of 1. So val should be 1. And the pointer should also be 1. So value of 1, and the pointer should also have an offset of 1. Okay, great. Now, again, we have prefix, decrement. So we're going to decrement the pointer first, which will bring it down here. It will be pointing at 0 when it gets dereferenced. So val should be 0, and the pointer should have 0 offset. So val 0, the pointer should have 0 offset. So why did we do the plus plus and the minus minus before we did our dereference? It was because the prefix plus plus and minus minus, increment and decrement operators have the same precedence as the dereferencing operator. So if we go back to our table, they are both precedence 2. Okay, that means that they will have to default to associativity to determine which one will be executed first. Right to left is the associativity. Therefore, we are going to do the right operation first, and then we'll do the left operation. So we did the plus plus and the minus minus before we did our dereference. Here we have them flipped. So now we have, again, they're both operating on the same pointer. However, they're reversed. So again, we have operators with the same precedence, and we have to rely on associativity, which is right to left for these operators. So we're going to dereference first. So we dereference P, and then we're going to increment that dereferenced value. So if we dereference P at this point, we're going to get 0, and then we're going to add 1 to it. So the value should be 0 plus 1, so 1. And the pointer never got changed. It never got operated on. So the pointer will stay right there. So we'll get a value of 1 and an offset of 0. A value of 1 and an offset of 0. Good. Okay, so now we have plus plus asterisk P. So we have prefix, increment, and we have a dereferencing. Again, they have the same precedence, so we have to rely on associativity, which is right to left. So we're going to dereference P first, and then we're going to increment. So we dereference P, we get a value back, which is 0, and then we add 1 to that. Okay, so we go from 0 to 1. So val should get the value of 1 assigned to it, but we haven't changed the position of the pointer. However, we have changed the value of the array in the position that's pointed to. It went from 0 to 1 here. So we incremented this value from 0 to 1. So we got value 1 and offset 0. In this last step now, we have, again, right to left associativity. So we're going to dereference first. The value of the array that's dereferenced, though, is now 1. So we have a value of 1. And we're going to subtract 1, decrement, from 1, which gives us 0. So val should get 0, and we should have the pointer still pointing to the first value of the array. And sure enough, we have that. We have val being 0 and the offset being 0 still. So that's a pretty complicated example that's using a lot of higher order interactions. No worries if that was a bit challenging for you. Getting the general idea is the important thing here. So that's all I have for you on this lesson. We'll pick it up next time. See you then.